Thank you, Will. Good morning. Is it a real problem, the problem of overheating nanocities? Actually, we have more than 13,000 overheated cities, according to recent data. Also, there is about 1.7 billion people that lives under very severe overheating conditions. Since 1980, the number of overheating hours has increased by a factor of 3. Is it really the problem of local overheating important compared, for example, with the problem of, let's say, global overheating? Is global climatic change more important than, let's say, local overheating? I prepared an example for you. I got a station close to the airport here in Sydney, and I report here the number of not working anyway, of cooling degree hours in the areas. We had about, let's say, 820 cooling degree hours in 1980. 40 years later, in our days, the number of cooling degree hours in the same area, which is not really urbanized, has increased by a factor by, let's say, 33%. This is the impact of the global climatic change, because in this area we don't have any urbanization. So because of the global climatic change, the cooling demand, almost the cooling demand in this area, has increased by 33%. However, if we move, let's say, inside Sydney, and let's take, a station not in the center, a little bit in the western part of Sydney. In this case, the number of, let's say, cooling degree hours is to about 81% higher than, let's say, in the coastal area, which means that really it is 3 times higher than really the impact of the global climatic change. But if we take a station in the far western Sydney, the number of overheating hours is to about 300% higher than in the coastal area. This means that really the impact of local climatic change, it's really tremendous and much, much higher than the impact of the so-called global climatic change in cities. Given that in our days, about 60 to 65%, and later about 80% of the global population will live in cities, we understand that the problem of overheating is much more serious than the problem of global overheating, and it needs to have our attention. Which is the impact of local overheating? Do we know the impact? Of course, during the very last years, there is a very, let's say, serious research that has been carried out to document the impact of, let's say, higher temperature in cities. First, we know, for example, the energy impact. It increases the energy consumption for cooling. It decreases the efficiency of power plants. It increases the peak electricity demand, obliging utility to build additional power plants, and we will discuss about it. But it's not just the energy impact. It is more, let's say, the environmental impact. Why? Because it increases tremendously the emission of pollutants from the power plants. It increases the concentration of ground level ozone, which is a killer. It increases the, let's say, the percentage of heat-related mortality and morbidity. It creates huge mental problems. We will discuss about it. But at the same time, there are many hidden, let's say, impacts. For example, there's a tremendous impact between overheating and productivity, human productivity. It increases tremendously the risk of accidents. And at the same time, it really plays a very important role regarding the survivability of vulnerable population. Do we have data? Can we really quantify this phenomenon? Do we have really enough evidence really to convince about this impact? Of course. As it concerns the energy consumption, and especially the increase of the energy consumption for cooling, we know very well now that in average, from real data, not from simulations, the average penalty that each one of us is paying because of the overheating of cities is close to 240 kilowatt hours per year. So each one of us, in average, is paying 240 kilowatt hours per year because of the urban overheating. However, in my opinion, this is not the most important of the impacts. The most important and the more, let's say, serious problem that we face because of the urban overheating, it has to do with the increase of the peak electricity demand. Because of the very high temperature, we need to use more air conditioning. If you see the penetration of air conditioning in Sydney is really exponential. Exponential. This obliges utilities to build additional power plants to satisfy the demand. But these power plants operate just for 1 month per year. We don't need these power plants during the rest of the period. And this has a tremendous impact on the cost of electricity because we made investments which are not used, and this increases the cost of electricity. On the other hand, we know that one temperature, the ambient temperature is increasing by 1 degree, the efficiency and the generation capacity of the, let's say, thermal and the nuclear power plant is decreasing by, let's say, 0.6% per degree. So during the day, with, let's say, a heat wave of 10 degrees, the efficiency of the power plants may decrease by 6%, which is very high. However, the real problem of, let's say, overheating concerning the energy impact is not the increase of the peak electricity demand and the increase of, let's say, the energy consumption. It is more the problem of the cost of electricity. Give you 2 examples. Last year in the UK, during the heat wave, in 1 day, because of the problem of the grid, the cost of electricity has increased by 5%. 5%, you may tell me, it's not important. It is very important. But the worst, it happened the same time in France. Because of the high temperature of the water, in the rivers, which is used really to cool down the nuclear power plants. The nuclear power plants really operated at high temperatures. In this case, their output and the generation capacity was very low. The result, the cost of the peak megawatt hour increased by a factor of 10. 10 times higher the cost of electricity. And this brings us to the major problem of the future regarding really the electricity. While in the previous years, everyone said that we have to decarbonize, we have really to minimize the CO2, whatever. This is important, but it's not the only target. The target is to decarbonize with, let's say, affordable prices. If you forget that, you will have a terrible penalty. For example, if you see the report of the European Union regarding, let's say, the future energy consumption and the cost of electricity, in 2022, the average, let's say, cost of energy, let's say, in Europe was about 12% of the annual income of the household. 12%. In 2050, the European Union is expecting to decrease the energy consumption by 80%. So households will use 80% more electricity. The report says that by 2050, households have to pay 18% of their income for electricity, which means that they expect a huge increase of the price of electricity. So it's not only to decarbonize, it's to decarbonize, be affordable, and has an added value for the country. This is extremely important, and this is forgotten many times. And this will have a tremendous penalty for those that they forget really the financial and the economic really impact of decarbonization. But unfortunately, as it concerns the energy, it's not only that really we'll have to install new power plants and we'll have really to decarbonize. Unfortunately, at the higher temperatures, affect very much the stability of the grid. For example, during the last 3 years, let's say in the United States, because of the high temperatures, the problems of, let's say, blackout have increased by, let's say, 150%, which means really that a huge part of the population may stay without electricity for many days. As an example, I'd like to show you what has happened, in June of 2021 in Pacific Northwestern in United States. Because of a blackout for 4 days, we had 600 additional deaths. We had about 3,500 emergency hospital, let's say, admissions, and hundreds of thousands of people without electricity. And this brings us to the future, let's say, objectives for the building design. Until now, we always said that we have really to minimize the energy consumption in buildings. Of course, we have to do it. It's not enough anymore. It's not enough because the main, let's say, objective should be the so-called passive survivability. We have to prepare buildings that really will operate and protect the health of people under very high temperatures, extreme conditions, without air conditioning. You cannot rely on air conditioning in the future. This is a big mistake. And this is very well addressed in the new European, let's say, legislation for buildings voted 3 days ago by the European Parliament. In the new European legislation, all new buildings by 2000 and all the retrofitted buildings have to be zero carbon. Okay, this was expected. But this new directive, it says that 2050, all new buildings and new retrofitted buildings have to prove the, let's say, so-called passive survivability. You have to prove that the building will not have temperature, will not really have indoor temperatures higher than 32 degrees during under extreme conditions without air conditioning. This is very important. And this really sets some new targets for, let's say, the building design. This is in brief the energy input. On the other hand, we have very serious environmental impacts. For example, because of the higher temperatures and because of the, let's say, reactions in the atmosphere, photochemical reactions in the atmosphere, we have a tremendous increase of the ground level ozone. Ozone is a killer. A recent report published in China shows that, let's say, during the last 15 years, the concentration of ground level ozone in the 100 more, let's say, important cities of China has increased by 80%. If you check the variability and the evolution of the ground level ozone in Sydney, you will be terrified. It's huge. It's increasing continuously, which is almost neglected. On the other hand, we know very well, and this is very well, let's say, documented, that for each degree of temperature increase, the emission of pollutants by the power plants is increasing by 3.5%. So during a day with temperature of about, let's say, 10 degrees higher, heat wave, power plants emit 35% more of pollutants. Apart of the energy and the environmental impact, there is another impact which is extremely important. The impact of urban overheating on low-income population. In general, we know very well that about 25–30% of the population is, let's say, of low income. Low-income population is living, let's say, in the more deprived cities of the deprived parts of the cities and in buildings which are not really well protected. As a result, they need to have a high energy consumption, but they don't have the income to do. On the other hand, because of the lack of income and because of the, let's say, lower quality of buildings, unfortunately, they live under, let's say, non-acceptable conditions. Reports show that, for example, in Europe, which is well developed. Low-income population, for example, in Portugal, is covering only 2% of their cooling needs. What's happening in Australia? We measure with the government of New South Wales the the indoor air conditions in about 110 low-income houses in Western Sydney. Not during a heat wave, during a normal summer day, indoor temperature was more than 40 degrees. And the worst, because people is closing doors, windows, etc., indoor concentration of CO2 was 4 times higher than the threshold. So low-income population, and there are thousands of data all around the world, lives under very high temperature and under very high pollution. And this brings us to the more serious problem, of the social impact of urban, let's say, overheating. There are many studies, usually, in the United States, that shows the social impact. For example, this study that was published, I think, a year ago, shows, for example, where, let's say, poor people in the United States used to live, and which are the climatic conditions in these areas. If you check this slide, you will see that Hispanics and Black population, they live in the areas of very high temperature. While, let's say, people of white people or rich people, they live in the cooler part of the cities. Another recent study, let's say, in Los Angeles, showed, for example, that the surface temperature in the areas where, let's say, the low-income people is living are to about 7 to 8 degrees higher than the areas where, let's say, the white people is living. And there is another study that was published 3 days ago that shows that heat-related mortality in the polar population in the United States is to about 30% higher during the same day than for the white population. And this brings us to the major problem, health, which is already discussed. Heat-related mortality and health is not a linear correlation. It's not an association of temperature. It is really a correlation with the association of many parameters. For example, it has to do with demographic parameters. It has to do with socioeconomic parameters. It has to do with, let's say, the health infrastructure in the area. We have data from all around the world, but mainly from the developed countries. We don't have data from the developing countries because they don't have the statistics. And we know that in the developed countries, actually, those that they are living in, let's say, the warmest part of the cities, they have 6% higher risk of mortality than those living in the cooler part of the cities. This is the average in the developed countries. And once really we check the forecast and the predictions about heat-related mortality, in the world, and this is from Lancet, you will see, for example, for the areas of Southeast Asia, or let's say South America, or even Africa, the expected increase of heat-related mortality is huge. So this is a very serious problem that we have to expect in the future. However, something which is not really well understood is the impact of higher temperatures on mental health. We know very well that during, let's say, the period of higher temperatures, aggressivity is increasing tremendously. It's increasing by a factor of 3. But what was not very well known is the association between temperature and, let's say, mental health. If you see this slide that was published some days ago in Nature, you will see that once the temperature is increasing, the problems of schizophrenia and the problems of mood disorders increase tremendously. So there is a huge association between higher temperature and mental health. And if really you want to see what's happened, for example, in Australia, see these results from Adelaide. The problem of mental health, hospitalization because of serious mental health problem against temperature, is an exponential increase. The actual forecasts about, let's say, mental health, the budget that has to be spent for mental health, shows that while today the let's say the budget is close to 2 billion all around the world for mental health problems, is expected by 2030 will be 35 billion. This is a very serious problem because it affects very much the quality, let's say, of people and the quality of life of people. The other important thing that we neglect is really the impact on, let's say, outdoor workers. Injuries, because, of higher temperature, increase tremendously as a function of temperature. And this decreases actually the productivity. For example, we know very well from statistics coming from the United States that the cost of higher temperature is about 100 billion annually in the United States, just because of the labor, let's say, loss of labor productivity. And the increase rate, the increase of the GDP in the United States is really decreasing by, let's say, about 0.25% per degree of temperature increase. So you understand that this has a tremendous impact on, let's say, the economy. But what is really very important is this relation between productivity, human productivity, and temperature. Studies that have been carried out with millions of people all around the world shows that when temperature is above 30 degrees, human productivity may decrease up to, let's say, 60%. Recently, let's say during the heat wave in Delhi, where temperature was above 50 degrees for 4 days, human productivity in Delhi and in India has decreased by 95% officially. And you understand what this means for a country to decrease the productivity by 95%? It's a tremendous real problem. What about the future? What really we expect for our cities? We know very well that we expect a very important increase of the nighttime temperature. Depending on the area, we may have an increase of the nighttime temperature between 4 to 6 degrees. And this is tremendous, not because of comfort problems, but because this will increase the nighttime temperature of buildings. So the day after, we start for higher temperature. So there's a continuous accumulation of heat. What about the daytime temperature? We expect a lower, let's say, increase, 2 to 3 degrees. It's not so low, but this is really what we expect. So the future shows us that we may have much higher temperatures really in the environment. And it is already discussed. The future about, let's say, the construction future shows that actually we have really a shortfall of about 330 million homes in the world. And this will be about, let's say, 440 million by 2025. As shown by Phil, I think, before, there's a tremendous construction, let's say, wave around the world. Just to understand, we build a new Paris per week. This is what we're building. We build a new Paris per week. And this brings us to the major problem. And the major problem in the future is cooling. Actually, the energy consumption for cooling is quite low, the red line. But one really will take into account the problem of global and local climatic change, the increase of the population, the increase of the GDP, etc. By 2050, the cooling consumption may increase by, let's say, 2,000% if we really will continue this way. A recent report published by DOE in the United States says that the cooling energy consumption of a simple Indian city, Mumbai, will be higher than the total energy consumption of the United States. Can you understand the impact of, let's say, this development in India? How many new stations? Which kind of station? Which cost of electricity? What's about the pollution? What's about the emissions? These are major problems that we have to face regarding cooling. And these are the bad news. I try really to present you the actual situation. Do we have good news? Of course. During the last 20-25 years, there's a tremendous research carried out all around the world. Edward has presented some very important results, trying really to decrease the temperature of cities and really help to have more sustainable, let's say, built environments. I don't have the time to go through the mitigation technologies, but I'd like to show you some developments that we have, let's say, were responsible here in UNSW. And this has to do with the development of, let's say, more advanced materials, especially the so-called supercool materials. These are materials which really present a very high reflectance, 96, 97%. But the most important is that these materials, they emit in the atmospheric window. So what? The emission of these materials can escape directly into the space, which means that we can send all the heat of the materials to the space, not to the atmosphere. These materials are developed here in UNSW. And I show you, for example, these are composite materials called photonic materials or daytime radiative coolers, which are composed, by, let's say, some special, let's say, ingredients which increase the reflectance and increase the emittance in the atmospheric window. I don't like to go and show you details. I like to show you the results. We tested these materials for, let's say, a long period in, let's say, Alice Springs, under solar radiation of about 1,000 watt, very high temperature during the day in summer. These materials under the sun present 6 to 7 degrees subambient temperature. It means that these materials have 6 degrees lower surface temperature than the ambient one. These materials are natural air conditioners without spending, let's say, 1 kilowatt hour. And the development of these materials has progressed together with UCL in London. We have developed a new material, which is a simple paint, that really can be extremely cheap. And when really applied in buildings, and these are the results of the testing in, let's say, Alice Springs, may provide and may, let's say, keep the surfaces of the, let's say, the buildings, roof, facades, etc., up to 4 degrees below the ambient temperature. So this is really a natural air condition. And of course, there are problems. Why? Because when these materials are used, for example, in temperate climates, may increase the heating demand. So we need to decrease, let's say, the reflectivity of the materials, and if possible, to have materials which during the summer provide cooling, but during the winter provide heating. Is it possible? Yes. How? We have integrated into these materials fluorescent, let's say, techniques, and fluorescent, let's say, quantum dots. What's special with the quantum dots? Quantum dots do not absorb heat. While, for example, when solar radiation falls on this material, will be absorbed and the temperature will increase. But once solar radiation falls on quantum dots, it is absorbed and immediately it's re-emitted. So the temperature is not increasing. And the other thing is that they emit a different wavelength. So they provide, let's say, color. We have developed these materials, photonic fluorescent materials, which means that we don't need to use pigments which absorb heat and increase the temperature. We provide, let's say, color by using fluorescent materials. So we can have color materials which have very low temperature. We have tested these materials this summer in Alice Springs, and what is impressive is that color materials, red, yellow, green, present exactly the same temperature like the, let's say, white photonic materials, those that they have subambient temperature. But the most impressive is that these materials, color materials, red materials, they present 4 degrees lower surface temperature than the conventional white. This is a breakthrough. Gold materials always have higher temperature than the white because they absorb more. These materials, they have 4 degrees lower surface temperature than the conventional white. So there's a tremendous progress that has been achieved really during the very last years regarding the development of materials. And you may ask me, how do we really try to implement these materials? Yes, this is what we are doing in Riyadh. We're responsible for the fall mitigation strategy of Riyadh. And actually, we're implementing these materials, in the roof of the buildings. Together with Berkeley University, we have developed all the super simulations in the area, including 3,323 buildings. And we have found that by implementing these materials, we can decrease the peak temperature of the city up to 4.5 degrees. 4.5 degrees, in a city like Riyadh, means that we can decrease the energy consumption, the huge energy consumption in Riyadh, by 35%. Just by implementing new materials, in the built environment, we can decrease in cities like Riyadh the energy consumption by 35%. At the same time, the study that we have performed on behalf of the Ministry of Industry here in Australia shows that, for example, the implementation of these materials at the building scale and at the city scale, for example, in Sydney, may decrease the cooling load by about 50%. And this is very well documented also with experiments. But the most important is that when these materials are used in low-income houses, may decrease the peak temperature during summer up to 10 degrees. And these materials, have been implemented, measured in thousands of, let's say, examples. And actually, there is a national program in India trying really to implement this. So, I'd like to conclude. We have a serious problem. At the same time, we have a very serious progress. Why we don't implement this? Why you use always simplistic solutions? Plant 2 trees here and put some grass there. It doesn't help at all. You don't have any results. We spend money without really doing nothing. Because the decisions are not taken really by scientists, are not taken by experts, are taken by economists. And economists, they understand really the severity of the problem when we monetize the problem, when really we monetize the cost of the problem. So it is really time to monetize the cost of the problem. Until now, we try really, and this was the main objective, to decrease the energy consumption of buildings, design a sustainable way. We have to do it. It's not enough if we really like to solve the problem. We have really to put a cost on the overheating, which means that though that they increase the temperature of cities, they have to pay. And those that they decrease the temperature of cities, they need to have credits and benefits. So we have to develop a mechanism like, for example, for the carbon credits in cities. And those that they increase the temperature of cities, for example, the councils that they put asphalt, black asphalt everywhere, like 100 years before, because they don't like to understand, and they increase the temperature by 2-3 degrees, they have to pay the credits. Those that they build settlements without really taking into account the impact of overheating, they have to pay the credit. They have to pay the cost. And those that they decrease the temperature of our cities for different, let's say, using different technologies, they need to have, let's say, the benefits. So we need to create this kind of exchange and make, a new credit mechanism in cities that really will help to further produce or further advance, the problem of overheating. I'd like to conclude. Actually, we have a very serious problem. And this problem is very well documented. Unfortunately, while it is documented, while it is, the scientific knowledge is very well advanced, in most of the cities, they use simplistic solutions. They like simplistic solutions. They like those that they give them, easy solutions without any results. Finally, this means that the impact of overheating and the strength of overheating is increasing. And the cost is increasing at the same time. So it is time the advanced scientific knowledge to be implemented really in cities. If we don't do that, we will not have results. We will pay a huge budget, and at the end, the temperature will increase. And this is my last slide. It's not enough really to develop technology. It's not enough to have financial, let's say, mechanisms. We need really to reorganize scientific research. Why? The problem of, let's say, climatic change and in general, the environmental problems and energy problems in our cities are multidisciplinary. Actually, we have a group working on energy, some other people working on environment, some others work on pollution. There are some epidemiologists, there are some others that they are doing economic studies, etc. There is no communication. There is no holistic approach. So the message that we send to the decision makers, is not the proper one. So there is a need, especially for the built environment, to organize, holistic approaches and integrated approaches of research. We have to consider all together in a holistic approach in order really to find solutions. And the message is clear. Once really we start to implement in a serious way mitigation and countermeasuring, techniques for the urban environment, this can be the most important productivity engine to drive growth in the future. Thank you.